Yeah, so let's continue. And after rescaling the rescaling and resizing the images and doing some data augmentation, what we are going to do now is building our model. And like I said, it's going to use convolutional neural networks, and we're going to stack our layers. We have the the convolutional layer, then we have the pooling layer, and then we're going to stack it, then we're going to flatten it, and have a dense layer, and so on. So that's what we're going to do. So the first thing, we're going to define this model that we're going to use the keras sequential to define, to stack the way we want to stack our layers. So we're going to use model that's sequential. So this model that's sequential is just, let me show you the sequential. So this, when you use the sequential model, it's appropriate when you want to stack some layers where each layer has exactly one input tensor and an output tensor. So that's what you're going to use. And okay, so I'm going to start this. And then now let's get our what it takes as an input. So the first thing, guys, we want to resize and rescale. So when an image comes in, it's going to be resized and rescaled before we take it to a convolutional layer. So we're going to resize and rescale. Then we're going to do some data augmentation. It's going to be either rotated, flipped, and so on. And then after this is when we define the convolutional layer. So we're going to define our convolutional layer, and first let's see what this convolutional layer from the documentation. Let's see what it takes. So yeah, let me see. So this comp2D layer, these layers, what it takes is that it has to have filters, the kernel size, the strides, the padding, and so on. So for our case, let's see what we're going to do in our so we have to have these filters. Let's go back to this. So like I said, we're going to do have these arguments like the convolutional, the spatial convolutional of our images, because we want to do it in the convolutional way. So let's get that. So what it takes is that it has to have filters, and these filters, like as if you have, maybe let's say you want an image of a car, so you'll have to define filters. I mean, this is a filter that will detect a tire. This is a filter will detect a windscreen, and so on. So in this, it's just like trial and error. So like you have, let's say you have 32 filters. And the good thing about convolutional neural networks, it will figure out these filters. So the next thing we're going to define from this, from the documentation, is that you need to define the kernel size. So the kernel size is the filter. We're going to define it's a filter. So again, let me share. You can remember from this is that you'll have from the convolution, you have a filter. Then that filter, then you have a feature map after doing some matrix multiplication, dot multiplication. So this filter is a 3x3 filter, and that's what we're going to do also in our model. And so we're going to define a 3x3 filter. Then we're going also to define the activation, because it's a, again, let me share again what we're doing. Because we're going to have a convolution and ReLU. So this is the activation function. Then we go to a pooling, then another convolution and ReLU and pooling. So that's how we're going to stack these layers. And so yeah, so this is going to be stacked with an activation. We're going to define our activation as the activation function that we're going to use is the ReLU. After that, we're going to define what will be the input shape. So like from this documentation, that you need to define the activation, You also need to define activation. You need to also define the input shape. What will be our input shape? So let's go back to this input. So our input shape, it's going to be the images, which is the image size 256 by 256. But let me just define it because we're going to pass other parameters. Let's just say input shape is equal to input shape, and we can define here what is input shape. What does it take this variable? What is it? So our input shape has to take has to get the batch size, or even it has to get the batch size. It has to get also the image size, which is 256 by 256, and then the number of channels. And because we are dealing with covered images for this example, meaning that the channels, and I have defined the channels as 3, as this is the part where I design. So we have the image size, we have the batch size, we have the channels. So that's defined. And then, yeah, so that will be our input shape actually. Then from the input shape, we have to go to the, after the convolutional layer, we go to the pooling layer. So we're going again to define the pooling layer. And we're going to use maximum pooling, which gets the maximum value as you move the filter across the layers, the arrays. And one thing also you have to notice, this is the pooling layer. It has to take the pool size, which is the number of filters. So you need to define the pool size, which is, you can say it's a 2 by 2. So yeah, so it's a 2D, so it's a 2, and we're going to say it's a 2 by 2. So that's the first convolutional layer, and it's the next layer is the maximum pooling. So we can also get another layer. So we can have, because we're stacking these layers like we saw in the illustration. So we're going to have another convolutional layer. It's COM2D. And by trial and error, again, these filters are just trial and error. So you can just see what will work. And the kernel size is just the same. The kernel size is 3 by 3. Matrix is a filter of 3 by 3. And then the activation is also ReLU. So we just want to make this. So the activation is ReLU also. And then you have another pooling layer of maximum pooling. So yeah, we can stack these layers as so we can have these layers. Let's just have uniformity, and we can stack these layers. Like you can add other like 5, or it depends on what you are doing. So I'm just going to like copy these, like we had copy them. So I have just copied these layers, so you can see like you have stacked layers of 64 filters and so on. Have a maximum pooling layer, another convolutional, and so on. So this is the convolutional pooling layers. Now from our examples, from the example, after having this convolutional layer and with the ReLU as an activation function, you have to flatten it, and then you can have a fully connected layer and so on. So that's what you're going to do again. So yeah, let's go back to our code. So what we're going to do is that after we have the layer to flatten it. So layers. We're going to flatten it, and after flattening, we can have another dense layer with the ReLU as an activation function. So it's also going to have 64 neural networks, and we can have this as the activation to be ReLU also. So this will have ReLU as the activation function. Okay, we're just building from that architecture that we saw before. And then we can have now the last layer, which is also a dense layer. And but here we're going to define the number of classes, which means that the number of classes that we want to predict. So let me call it number of classes, and I will define that. So number of classes, the activation, because it's we want to predict 3 classes. So I'm going to use this is the output layer. So I'm going to use the softmax activation function to give me the probability distribution of these. And yeah, that's pretty much yeah, we need to define this number of classes. We have 3 classes according to what we did before to get the classes. So we have like 3 classes here. Yeah, and that's okay. So we have had layers stacked, which is the convolutional layer and the maximum pooling layers. And we also have these, we flattened it to get the, and then we have used this dense layer and the softmax as the activation function. Yeah, then according to this, we have to build a model then. So we'll build a model using model.build, and we're going to use the input shape. So our input shape is for the input shape, just this. We're going to get the input shape. So yes, yeah, we can then run this. Yeah, so we need to define that this variable to be model equals to this, and then we can run our model. So yeah, so that's how you do it. Then now we can get summary of our model. So we're going to check the summary or check the what is in our model. So we're going to use check the get summary. Just get the summary of our model. And from the summary, there's the summary of the model. Like we want to see how many how many trainable parameters are there and so on. So we can use model.summary. So we can run this also. So this gives you our models like the layers, the convolutional layer, and the pooling layer, and so on, and how many trainable parameters that we have in antennas. These are like the weights, okay? These are the trainable parameters. So after getting the summary, it's when now you can start. Now, how are we going to compile our model? Because we have the have the architecture already. Now we're going to get how we are going to compile our model. And compiling our model is just getting this. The next thing I will do is compiling our model. And with compiling our model, we need to define how the optimizers, we need to get the loss function as well as the metrics which determines the performance of our model. So let's get our function using the model.compile. So the loss function just checks in the prediction of the error in our neural networks. So, and then we're going to define the loss functions and so on. So one of the things is we're going to get the optimizer. So one of the famous optimizer is Adam. It's faster. There are many optimizers, but Adam is one of the popularly used, and it's fast in operations. The others like stochastic gradient and so on. So we have the optimizer. And then we also need to define the loss function. So there are also loss functions. They just check they predict the error between the real value and the predicted values. So they check the error. So we're going to use also. So let's say loss equals to, let's define, and yeah, we can define it as our loss is df dot keras. We're going to use a cross entropy as the loss function. And before going, we can check it. Also, we can check the documentation. So, yeah. So these are losses to check the, so this we're going to use actually this one. So it computes the cross entropy loss between the labels and the prediction. So that's what we're going to use. Let's copy it. So it also has to what it takes. And you can also see it's the argument that it takes. Here, logics is just checking if your outputs are normalized. So we have the softmax function. So our output is already a probability distribution and it's normalized. So we're going also to use this as false. If it's not normalized, if you haven't used any softmax function, you can put it as true. In our case, it's false. Yeah, and another thing is we are going to define our metrics. Our metrics is and our metrics is accuracy. So let's messed up. So let's get something that is. So our metrics is going to be accuracy. So we're going to check the accuracy of our model. Okay. And yeah, so that's how we're going to compile it with the optimizer and so on. So let's run that. Yep. And yeah. Yep. Forgot the commands, so we can run that. Yeah, so next thing we're going to, what else we're going to do? We're going to get how we're going to fit our model, like train our models given the data set, the training data set that we have, and also check its accuracy using the validation data set. So we're going to use model.fit. So let's just, let me comment this here. Like we're going to train the model using the data set that we have. So we're going to train the matrix with the given input metric. With the given input and the corresponding actually and the corresponding label. So we're going to use the model.fit. So we're going to use model.fit. So what the arguments that it takes. The first thing we're going to say we're training it with a training data set. So training, and the training data set we already defined it. The next thing we're going to get the epochs, the training iterations. So these are the epochs, and from what we have already defined that our epochs are 50. And then what else we're going to get is the batch size, and also our batch size is already so our batch size is already specified. So let's get our batch size. Is batch size, and the batch size is 32 already specified. Another thing that we're going to do is that we need to get the, because we want to see this model as it trains. So let's say verbose is 1. If you put 0 meaning that you want to see it, so verbose is 1. And also we get to get our validation data. So our validation data is just to like check as we train, we check the performance of our model. So our validation data is equal to the validation data set that we already from the functions, if you and remember the function that we created that divided our data into the train, test as well as validation data. So yeah, and one thing also, we're going to feed this in a parameter called a variable called history, so that we can be able even to plot it to plot some graphs out of this. Okay, so that's the essence of this. So this is because we're training here, this is going to take some time, and it's going to like it's going to take a lot of time, depending also with the speed and the hardware and all that. So let's wait for it to finish training, then we can continue how in evaluating our model. So we're going to wait for it to finish training all the epochs. There are 50 epochs. You can use even you can use it for them. If you're training, you can even use less epochs. Like for now, just use 50. Then we're going to wait for it. When it's done, then we're going to go on with the model evaluation. So yeah, so we're going to wait it for to finish.